Hey guys, how you doing? Let's remember we're always in the holy presence of God. This is Coach Scott at Christian Brothers High School, and let's talk about stoichiometry using BCA tables. But now let's look at BCA in relation to limiting reactant, which can be a little bit more difficult, but not really. Not because you guys have the basics of how to use BCA with limiting reactants, or with the tables with those proportions. So now let's look and see the stuff with using a limiting reactant problem. So most of these problems, all right, they will give you reactant. Yeah, there we go. They will give you the masses or the liters or the moles of the two reactants. So they're going to say which one limits the reactant. Which one is the one egg out of a 2-egg cookie recipe, if you would. So, like any time in BCA tables, one, we have to have a balanced reaction. And again, most of ours will be balanced, but you got to be prepared. And then, of course, everything has to be in moles on a BCA table. Okay, everything in moles. So let's throw a reaction down. Let's do the one we were doing on the previous video. So we've got 8 moles of ammonia gas plus 6 moles of nitrogen dioxide gas. That's going to react and give us 7 moles, and these are balanced. 7 moles. 7 of, wow, it's early in the morning, N2 gas, and 12 moles of H2O, water vapor gas. Okay, so we might have a problem where they say, okay, you've got 50 grams of ammonia, and you have 60 grams of NO2. Which one of those is going to limit the reactant? That'll be the first part of the question. Well, of course, let's draw our BCA table out. We've already did this on the previous one, but let's draw it out real quick. B, before, the change, and after. Again, I like doing lines because, well, keeps my ADHD in check. Okay. So this gave me 50 grams, and this is on the left-hand side. So I've got to get it into moles. Remember, number 2, everything has to be in moles. So if I'm given grams on the left-hand side, then I have to divide, okay, well, whatever factor it is to get into moles. In this particular instance, we've got to divide by the molar mass. So the molar mass of NH3, we'll use 17. Okay, and I need to divide by the molar mass of NO2, which happens to be 46, 1 nitrogen, 2 ammonias. Okay, so I do that, and I see that I have NH3, I've got 2.94 moles of NH3. And then if I look at the NO2, I've got 1.3 moles. Okay, so now then I've got to use some logic here. That's given. Of course, there's 0 moles of products before the reaction. So in the balanced reaction, I have 8 moles of ammonia and 6 moles of nitrogen dioxide. So this number of moles should be less. But let's see if it should be, if I have enough of those. So if I was going to do this, all right, 2.94, all right, it should be less, so I'm going to multiply by the ratio of the moles. That will give me a small number. So if I multiply 2.94 times 8.6, that'll be a larger number. I don't want that, so it needs to be a smaller number. So I'm going to multiply 2.94 times 6/8 and see what I get. Okay, 2.94 times 6 divided by 8. And I get 2.25. I'm going to put that up there. 2.25. 2, 1, we'll say. Well, I don't have 2.21 of the nitrogen dioxide. I've got 1.3. So this cannot be the limiting reactant. We've got more than enough ammonia. So that means that my limiting reactant has to be the nitrogen dioxide. So that answers the first question. All right, nitrogen dioxide is the one egg. It's the one that limits the reactant. Okay, so let's see how much ammonia I need for 1.3 of nitrogen dioxide. In the reaction, all this will be used up. So I look at nitrogen dioxide. I've got 6 moles of that, 8 moles of ammonia. So that means I need a bigger number on this side. So I'm going to multiply 1.3 by either 8.6 or by 6.8 to give me the bigger number. Of course, I'm going to multiply 1.3 times 8 over 6, and that gives me 1.73. So that's how much is going to be consumed. Okay, so let's use the 1.3 to see how much of the nitrogen gas will be produced. Okay, so I'm going to, it's 7, so that should be a little bit bigger than 1.3. So I'm going to multiply 1.3 times 7.6, which will give me the bigger number, and I get 1.52, and it is bigger slightly. So I look at how much water is going to be produced. Okay, if I do 1.3 times 12 over 6, that's going to give me a bigger number, and it should be bigger. In fact, it should be 2 times the amount, and it does come up to 2.6 moles. So if I add all this up, I subtract, I'm going to have 1.21 moles of ammonia left over after the reaction. The nitrogen dioxide is going to be gone. I'm going to produce 1.52 moles of nitrogen gas and 2.6 moles of water vapor. Okay, so now if I wanted to, they're asking me how many grams of nitrogen. Okay, then I'm going to multiply on this side. They ask me how many liters of water vapor. I'm going to multiply by 22.4. They ask me how many moles. I'm going to multiply by Avogadro's number. I can answer all the questions with this table. And I can also make this a percent yield problem. Let's say, for instance, okay, that you actually produced 35 grams of water vapor of H2O. What's your percent yield? Well, I'm going to have to figure out my theoretical yield of water vapor. So I'm going to take 2.6, okay, multiply it by 18 grams per mole, okay, and that's going to give me a theoretical yield, or how much I'm supposed to make, of 46.8 grams. All right, so now all I have to do is divide actual by theoretical, multiply by 100, and that'll give me a percent yield, or how much I made compared to how much I was supposed to make, of 74.8%. Again, we did all that through the BCA table, and it's so much simpler, and I think you'll do very well on your test. So guys, this is Coach Scott saying St. John Baptist de La Salle, pray for us.